It's a great honor and great pleasure to give a talk on my recent work on TT-BAC related development. It's based on some recent paper I just posted on the archive at the beginning of this conference. So let me start with the general motivation. So for the most recent of your years, what I always have been, what's always have been in my mind is the following question. So we've learned so much from ADS CFT, but we don't really live in antecedent space-time. Is there a version of holographic duality that really works for our real universe? And if it works, how can we get started? How can we try to build it? And this question is shared by lots of other people as well. And I think I would like to say there are various approaches, but I can classify them as two types. One is the bottom-up approach, which is to say that, okay, we have Einstein gravity, which whatever the UV version of gravity is, its semi-classical limit is Einstein gravity plus matter, standard model, and we know where we live, and we know the effective field theory, and can we ask about certain universal properties of the putative due to this gravity. And there is another approach, which is the top-down approach. That is to say that at the moment, there is, we know, there is a very promising candidate of quantum gravity, that is string theory. So if I start from string theory, and I start from some known, from some well-established construction of holographic duality, and I do something, I do some deformation or perturbation whatsoever, that I can control from both sides of the duality. And if I can control the deformation on both sides, then I will land on some new holographic duality that is potentially related to potentially a toy model of holographic duality that beyond ADS-CFT. And this is the program I have been thinking a lot recently with lots of collaborators, in particular Luis Apollo here. I don't know if he's there, and Cui Wei here, and I don't know Juntao, and also my student Zheng Yuandu there, and Kangning Liu, and other collaborators. So we have to start from something that is well established. And luckily for us, there is a very good starting point. Actually, that was celebrated 2 years ago by the Fundamental Science Award, and the authors here, that's Matthias Gabadillo and Lawrence Eberhard and other collaborators, they set up a very good example of concrete, explicit, and holographic dual built from string theory. So in a holographic duality, there is a bulk theory and there is a field theory. In the bulk side, This is type 2B string theory with a factor ADS3 and some other 7-dimensional manifold. And in 2 years ago, Matthias told us the exact deal was established for type 2B superstring theory at the point where k equals to 1. And the dual theory, the field theory, the 2-dimensional field theory is a symmetric product. And a few days ago, he told us again there's yet another example. This is a bosonic string at k equal to 3. At both points, the holographic dual to the string theory is known, and we can they already write the theory down. And in both cases, the theory is described by symmetric product theory. And that's the starting point. We'll start from there and start doing some deformation from both sets of the duality. And in the field theory set, the tool we use is a talk in the other room just before this by Smirnov. And so this year's Fundamental Science Award was given to Smirnov and Zamilodikov for their work on TT-bar deformations. And he just gave a very nice talk on that. So that's the tool we are going to use. So in the field theory set, we deform the seed theory of the symmetric orbifold by TT-bar deformation. And after we deform the seed first, and then we do the symmetric orbifold. And this version of the TT-bar deformation is called the single trace TT-bar. So that's the deformation we're going to do in the field theory set. And now you can ask, if you do this deformation there, what's the bulk dual? What kind of deformation you are doing in the gravity set? And the answer is that, first of all, the background metric is deformed and completely. It is no longer ADS, not even asymptotically. Instead, the asymptotic structure is flat space in a string frame with a linear dileton. This is the so-called linear dileton background. And this is truly a non-ADS space-time. And you could ask, in the field theory set, the operation you are doing is the single trace TT-bar deformation. What's the operation you are doing in the gravity set, in string theory? The answer from us is that you do the so-called TST transformation. T refers to T-duality, S refers to a shift mixing two coordinates, and then T-dualize again. So I'll explain in more details what this whole story is about. And this is a bigger picture we have in mind. So we want to understand this deformation from both sets more completely and have a better picture of this conjectured duality for not for asymptotically flat spacetime. And so far, we managed to establish many agreements from two sets. We can match the string spectrum. From the gravity set, we can calculate the long string spectrum, how it is deformed by this TST transformation, and that is matched to the spectrum of the single trace TT-bar deformation. And then there's also the calculation of partition functions that can be matched. And we can also construct black holes in this background. And then the black hole entropy can also be matched. And 2 years ago, a new progress we found is we can, using the string worksheet calculation, we found a very simple structure of the two-point function in momentum space. So it's this formula here. So this is P and P bar are the two called momentum. And then the two-point function is given by the right-hand side. So what is this? So suppose you have a two-point function in CFT, and you go to the momentum space. In CFT, if the operator is a primary with conformal weight H, then that's precisely the two-point function. What's happening here is that after this deformation, the two-point function takes the same form as the CFT result. The only change is a shift of the conformal weight, and the shift depends on the deformation parameter lambda and the momentum. So we are in momentum space. So that's a very surprisingly simple result. And yes. No, it's not. No. It's exact. Well, it's certainly not perturbation, but there are some accumulator. So from the string theory calculation, this is a non-perturbative result we obtained. And like a few days or a few weeks or shortly after this, Haroni and Barrow, they did a field theory calculation in using they're considering TT bar deformed 2D CFT and using this passing integral formalism, and their calculation is very complicated. But in the end of the day, if they take this high energy limit, that is to say, you take the P and P bar to be large. In their paper, they said that if we take this momentum to be the highest possible scale in the theory, that's precisely the result you get. So this is the immediate motivation for my talk today. Given this simple structure from like both sides of the calculation, so you may wonder why is it so simple, and is there any symmetry behind it, and also we are doing this string theory computation, and they are doing this complicated TT bar computation, and it is not very clear whether we are talking about the same thing. Yeah. Oh, we are putting TT bar deformation on the plane. You can think that this is it doesn't quite matter the other directions. You can think that's just this case, K+3 case, the bosonic part. But of course there's if I decide to normalize my undeformed two-point function in momentum space to be just like 1 over x2h, then that's the result. If you renormalize it in other ways, it may differ. And P, so it's on the plane, and P and P bar are the momentum in the two null direction. Okay. So that's some result we got 2 years ago. So today, we are going to ask about symmetries. So what's the symmetry structure underlying this? And if there is if there are symmetries, how are they? How can we use them to organize the operators and organize the computations of, say, correlation functions? So the main result, if you want to go and or want to fall asleep, that's the upshot of this entire talk. So the answer is that after a TT-bar deformation of a 2D conformal field theory, the conformal symmetries, they are still there, but they are realized in a non-local way. And we can actually, we will show, we can explicitly construct the Virasoro generators. And using this symmetry, we can define a new type of operator, which is local, but still organized by this non-local conformal symmetry, and that help us to do calculations. And we'll show how can we get the two-point function that I said it before. And as you have seen, this is Liang Yu. Liang Yu is also here. And Zheng Yuan and Kang Ning, Liang Yu is a postdoc at Tsinghua, and Zheng Yuan and Kang Ning are my students. All of them are very brilliant, smart, and working hard. And Zheng Yuan is trying to get a job. So if you you want someone, please consider him. It's always there. It's you will see. The stress tensor, that's just two translational symmetries are always there. But by conformal symmetry, I'm seeing the full Virasoro generators. They can be constructed all the way at a finite deformation. Sorry. Yes, they are commuting. Yeah, we'll see. Okay, now that's the plan. So the first part, I give this big picture of TST, TT-bar correspondence, but the first part will focus on just the TT-bar deformation. I'll talk about symmetries, operator correlators, just from the field theory set. And then the second part, if I have time, I'll go to this TT-bar picture and see how things fit together there. Okay, so let me start. What is TT-bar deformation? Of course, Smirnov just gave a very nice talk on TT-bar deformation, but if you happen to be there in his talk, you can see different notations and different perspectives. Here, I will define TT-bar deformation as the following. So let's consider a family of quantum field series in 2 dimensions, and all these QFTs, they have 2 translational symmetries in these 2 directions, so that you can define the Noether current, namely the stress tensor. So as long as you have a stress tensor, then you can define a TT-bar deformation to that QFT. And it's defined as a differential equation of the action. It's the derivative of the deformed action at a deformation parameter mu, you take the derivative with respect to mu, and the right-hand side is the integral of this so-called TT bar operator. And there are many ways to write this TT bar operator. One quick way is to say, oh, that's the determinant of the stress tensor. Alternatively, you can also write it as like you can see it's a quadratic combination of the stress tensor. So by writing it in this way, you can see that if I deform the theory, deform a CFT has the trace of the CFT 0. So in that case, this is nothing but T, which is the left moving stress tensor, and T bar times T bar, which is the right moving stress tensor. That's where the name TT bar comes from. At a generic point along the flow, it contains 4 terms, not only T times T bar. It's actually, it contains 2 terms. Right? Okay, so this deformation, as you can see, is quadratic in the stress tensor in 2 dimensions. It has this deformation parameter has length squared, dimension length squared, and therefore this is an irrelevant deformation. And this people have shown, there are lots of people contributed in this work. It is shown that the theory is solvable in the sense that if you put theory on a cylinder with finite size, then the deformed energy can be written in terms of the deformation parameter and the undeformed spectrum. And this, as I mentioned before, for any 2-dimensional KFT, you can define you can define such a deformation. And for me, I am most interested in deformed TT bar deformed CFT. And if you were at the other talk, lots of people were originally interested in doing TT bar deformation for integral models. And let's any 2D QFT, you can do this deformation, and they share like lots of similar structures, and this deformation also preserves lots of nice features of the original theory. If the original theory is integrable, TT bar preserve it. If you start from a 2D CFT, you have modeling invariance, TT bar will also preserve it. This deformation also allows for various generalizations from different perspectives. You can generalize. So now we are doing a TT bar deformation. You can change, as I mentioned, the stress tensor is another current to 2 translations, right? And this is deformation can be thought of as a J-wedge, J-type deformation, where J refers to another current of U1 symmetry. So if you change the symmetry you are thinking about, and you can also get this JT bar deformation. And also you can mix TT bar, JT bar, lots of generalizations. And also there are also higher dimensional or lower dimensional generalizations. And so I wrote the theory on this slide in this form. But this TT bar deformation can be formulated in lots of different ways. In particular, in my next slide, I will formulate it in this Hamiltonian formalism. But again, since I'm a holographer, I would like to stress that the most striking property of this TT-bar deformation to me is that it is very useful to build holographic dualities beyond ADS, both in the bottom-up approach and also in this top-down approach. So now let's just go back to TT-bar itself. And as I mentioned, let's use this Hamiltonian formalism and look for certain details. So as I briefly mentioned that TT-bar deformation, you can think it as a bilinear product of two nodal currents. So here I wrote it in this form. So for TT-bar, this you can think this A as a label of the translation along XA. Then this and beta is the component of this current. So more generally, you can use A and B to label different UN symmetries, and this alpha and beta are space-time indices. And for lots of like UN generalized notion of UN symmetries, you can always construct such like G wedge G type deformation, and you can show that this deformation now in Hamiltonian formalism is expressed as the derivative of the Hamiltonian with respect to mu, and this derivative can be written in two terms. There is the first term is a commutator of operator chi with the Hamiltonian itself, and there is another term that's is this Y term. So the commutator term, if you act this the whole thing, this equation on eigenstate of energy, so the commutator term is actually is an off-diagonal term. And as we will show later, it is a canonical transformation, and it doesn't actually change your state. It doesn't change the spectrum. And the second term, this Y term, as we can see from here, it actually it factorizes into the product of two integrals, Y direction, this Y integral and Y prime integral. You can just perform them separately. And this term, if we act this on eigenstate, it's a diagonal part. So here we are putting the theory on a finite cylinder with radius r. So as we can see, the diagonal part is proportional to 1 over r. So if you consider finite energy excitation and take the r goes to infinity limit, this Y term just vanishes, and then the theory is left with this doing TT-bar deformation in the this on the plane just reduced to doing this canonical transformation. But before that, let's like review more about what's this doing. So if we this relation, if we insert this operator relation inside a state, energy eigenstate, and we take the expectation value, you see that the first term is a commutator, it's 0, it doesn't contribute. The only term that contributes is this diagonal part, and then we know the diagonal part is also written in terms of the stress tensor. And it's an integral of the stress tensor, and if we consider the particular components, you can see that actually it is this Y term is there are two terms. The first term is the Hamiltonian times the integral of the pressure. So Tyy is the pressure term, right? And this integral is nothing if we put this onto a state, eigenstate, it's nothing but the derivative of the energy with respect to the volume, right? And then the second term is the momentum along this y direction. The y is the coordinate on the circle. So this is this so-called implicit Burgers equation that's characterize this TT bar deformation. And this equation can be solved precisely if your starting point is a CFT, where your energy and angular momentum depend on the radius in a known way, and then you can just solve it. And that's here is the energy flow. So suppose at mu equal to 0 is the CFT point. So I just this is a diagram. I draw it with equal spacing in the energy level. It's just I'm not saying that this only applies to CFT with like equal spacing, but this is just to show how the energy, each level of the energy flows with the deformation parameter. As we can see, if this deformation parameter is positive, if you can, I'm not sure if you can see this dashed line. The dashed lines are the flow lines of this solution. So there is a special point. So when angular momentum equal to 0 and energy equal to 0, it doesn't flow. So the state with 0 energy doesn't flow, it's flat. And above positive, above 0, or the positive energies, if mu is positive, so as you can see, the higher energy states, they grow denser and denser. And this corresponds to this Hagedorn behavior at high energy. This is when mu is positive. But you may wonder, so we are considering a CFT on the cylinder. There is a special state which has negative energy, that is the ground state, right? And the ground state also flows. And it flows along, again, this dashed line. So if you stare at this formula, and if this is negative, you can see when mu is bigger enough, then what's inside this square root will become negative. And then there's a critical point of the deformation parameter. If it's too large, then your ground state will become complex. So that's the status of the spectrum with positive mu. Then how about negative mu? For negative mu, let's first look at the ground state. Nothing, very bad happens. But you can also see there is this red line here. The red line here is the line where whatever inside this square root equal to 0. So above this red line, what happens is that the energy, at high energy, when mu is negative, this energy after TT by deformation will become complex. So that's this key feature of the spectrum. And now this part is actually in this Hamiltonian formalism is already decided by this blue part, the diagonal part. But today, we're more interested in this red part. So for that reason, we want to take R to infinity. We want to put the theory on the plane. That means that, on the plane, this, the TT by deformation will not change the spectrum, but there is still something happening here, right? So what's this? So the first part is actually, now I'm switching notations. Lambda is my deformation parameter. So the Hamiltonian, the derivative of the Hamiltonian with respect to this deformation parameter looks like evolution by this operator chi, right? So it looks like this lambda looks like some like auxiliary time in the space of field series, right? So what this is doing in the field space is the following. So it introduces actually a canonical transformation, which means that suppose before the deformation, you have this canonical pair. Oh, sorry, I should put x, x and pi. So they are conjugate pair. Suppose they have the canonical boson bracket, and after this deformation, we can just change the coordinate p and x and pi. We can change the this on the symplectic manifold. We change the coordinate without changing the symplectic structure in such a way that such that the new coordinate still satisfy the same relation. So let's define this covariant derivative with respect to lambda with the connection this chi operator. So anything that is covariantly constant in this manifold will be satisfy the same sort of relations like along the flow. For instance, the boson bracket, and also for any actually arbitrary functionals of the this coordinate on the phase space, as long as this operator satisfy this covariant constant condition, or the this relation. Suppose there is a relation f of this coordinate is satisfied, then the lambda derivative actually will preserve this relation. The reason is that if since p and pi they satisfy this relation, they're covariantly constant, and then so that the relation will also satisfy that. That means that this relation, the derivative of this relation, is proportional to the relation itself. So that as long as it is satisfied at the starting point, and the flow will also preserve it. So for instance, if we have a conserved quantity, we have a conservation law. And satisfied the conservation law is a certain function of operators that satisfy this flow equation, then the flow will also keep this relation. So that allows us to define operators that along the flow, the so-called Dresser operators. They are defined as operators that are covariant constant under the flow with the initial condition that at lambda equal to 0, they agree with the undeformed operators. But before that, I need to say the first type of operators in this Hamiltonian formalism. So suppose we have a CFT at t equal to 0. We have a set of operators on the t equal to 0 slice, CFT operators. We take them, and then we evolve this operator to time t by the deformed Hamiltonian. So now we have a new Hamiltonian. So we will evolve the CFT operator at t equal to 0 by the physical Hamiltonian in our deformed theory. That defines the so-called undeformed operators. They are undeformed in the sense that they agree with the CFT operator at t equal to 0, and they are naturally evolved by the Hamiltonian of the theory. And then these operators, they by definition, they are local operators. But the trouble with these operators is that they are very messy. So if you want to do any computation using this, you need to deal with this Hamiltonian, and the new Hamiltonian is deformed. And as we have seen that it's like defined instantaneously, at each point of mu, your Hamiltonian is different. So if you do some perturbation, you not only need to do expansion in the explicit parameter lambda, you also need to deform, expand your Hamiltonian. So this so-called undeformed operators, they have the feature that they are local, but they are not organized by symmetries, and the computations of them are very hard. And the dressed operators, as we mentioned, they are solution to this flow equation, and at lambda equal to 0, they agree with the CFT operators. So that's the dressed operators. So from the definition, as we mentioned that, you see, this from this on the plane, we know T bar deformation. If any for any operator satisfying this covariant constant condition, they will have a very nice symmetry properties. On the other hand, as we will show explicitly, these operators are horribly non-local. They are very complicated. You can write it, but they are very complicated. That leads us to define the third operator, which is, we call it the physical operator. And it has the nice property that it is local. And as we will show later, it is a local expression in terms of this undeformed operator. On the other hand, it also obeys some symmetry properties, and we can use conformal symmetry to organize the computation of such operators. Okay, so how much time do I have? 10? Okay. So let's start with the stress tensor. Suppose we have this TT bar deformed, we have this action, and if we assume that this stress tensor is the standard Canada form, but in many examples, we know that this is not the true stress tensor. You need to correct it for various reasons. But if we assume this, then we can go ahead with lots of the calculations. And then we can as we mentioned, there are three types of operators. For the stress tensor, we have this undeformed operator. It agrees with the CFT stress tensor at t equal to 0, but evolved by the true Hamiltonian. They are undeformed, local, but this undeformed operator is actually, in the case of the stress tensor, is not our true stress tensor. The true stress tensor is the deformed one, and it is local conserved, but this is no longer a chiral stress tensor. So in the CFT, the analog of this in CFT is that left moving, right moving, chiral, anti-chiral, but the deformed one is no longer chiral, but still conserved. And then we can also define the dressed stress tensor. Like by definition, we need to solve this flow equation. We can do this explicitly at the classical level. I'll skip the details, but we can just do it, and this is the final expression. So the left-hand side is the dressed stress tensor. It is chiral, and it is the mode expansion of that will be the versor. But on the right-hand side is the infinite sum, and the worst thing is that it is not only an infinite sum, it is also non-local, because it is written in terms of this non-local coordinate delta u hat, which is essentially the integral of this stress tensor. So it's here HL is the deformed stress tensor, and delta u hat is some non-local thing. And so we can do the forward, well, as we can see, the name delta u hat suggests that we can define this u hat, which is basically u plus this delta u hat. And this is a non-local coordinate. U hat and v hat are non-local coordinates, and they are related to the original null coordinate in a complicated, in a way, basically it's the original one plus lambda times the integral of the stress tensor. And you can also reverse this relation, and the right-hand side can be regarded as u hat and v hat, but now I can define, use this sigma, and then define an arbitrary function of sigma plus sigma minus, and if I plug in the u hat here, so plug in, this is just the inverse function. So the u hat, capital U, uppercase U, as a function of little u hat and little v hat is just the little u. What does this mean? So there is, as I mentioned, there is yet another formulation of TT by deformation in terms of string theory. So there is a notion of worldsheet and a notion of target spacetime. And so we can intuitively understand this as the TT by deformed theory lives on the target space, and the coordinate are this little u and little v. And the sigma plus sigma minus can be viewed as the worldsheet coordinate, and there's a CFT living on that. But the worldsheet coordinate and the target spacetime, they are related precisely in this non-local way. And so now we can now define the stress tensor, the versor generators. Indeed, they satisfy commuting versor algebras. We don't see a central charge because we are doing a classical computation, and also we assume the a particular form of the stress tensor, which doesn't usually carry classical central charge. And then we can do a very similar thing to primary operators. And it's also very complicated, but again, you can solve this addressed operators starting from a highest weight operator in the CFT tool, and then you can define this undeformed operator and the addressed operator. Again, they have the similar property. Undeformed are local, but not symmetry organized. Addressed operators, they are non-local, but they are correlators, they are wide identities, lots of things. They are exactly the same as the CFT result. And in the middle, there is this, what we call this physical operator. It's related to the undeformed operator by multiplying it by certain factors that depend on the stress tensor. HL and HR are stress tensor. You can see this H and H bar showing up, and this looks like some sort of conformal transformations. It has some flavor of that. On the top, it's this combination, OTT bar is the TT bar operator. And this factor is related to, remember this non-local coordinate transformation. So if you look at the Jacobi, and this is the determinant of the Jacobi. And that's this physical operator. And it is from this, the fact, from this expression, it's obvious this is a local operator. There's no integrals involved, no infinite sum. It's a local operator. On the other hand, it can also be written in terms of this stressed operator. There's the intuition is that the stressed operator is some secret CFT operator living on some sort of auxiliary worksheet, sigma plus, sigma minus, and then you integrate that by this delta function. Basically, you pull this from the worksheet to the space-time, and then you get this physical operator. That's a simple intuitive understanding of this physical operator. And it's also, as we mentioned earlier, the Aharoni and Barrow, they studied some operator using this topological gravity formulation. And that operator, well, since our operator was first constructed at the classical level, and we can, at the classical level, we can just relate these two operators, and they match precisely. So that actually explains why well, our later computations could be related. And then in order to do correlation function calculation, we need to uplift our classical defined operator to quantum level. Here we don't know all the details. We just assume that there is a way to properly normalize the operators so that at the quantum level it still looks like this, and this it satisfies certain flow equation. This is different from actually in the literature. Lots of people study correlation functions, and most of them are actually studying the analog of the undeformed operators that we discussed before. So they are clearly different. But for this physical operator, we can do something better because if we, here is an expression in the momentum space. As you can see, everything on the right-hand side is the dressed operators. And as we mentioned, that it looks like it lives on some auxiliary CFT coordinate. And then you can just, because these operators, they satisfy inside the correlator, these operators and all these stress tensors, stress tensors, they satisfy the same CFT results. So we can just use it. And when we do computations, we can do series expansion in lambda. But now this lambda is explicit. Nothing else depends on lambda. Then we can just do this, use repeatedly the wide identity and the CFT correlators. So that's the result. We have smart graduate students who can do the computation. And the result is that we can expand it. And at each order, this correlation function, you can separate them into 3 pieces. The first, the blue part is the safe part, which is the undeformed CFT correlator. And there's a green part is just the boring Taylor coefficients. And then there's also this purple part. This is a polynomial in log x. And what we know is that it is nth order polynomial, and the leading coefficient is always 1. And this term is universal. And if you consider UV behavior, this is also always the dominant piece. And if we only consider this part, we can sum it all over. So this is a non-perturbative result. This result we saw at the beginning. This is a non-perturbative result in the deformation parameter lambda, although it picks up the most UV sensitive piece in each at each order, and that also explains why the computations we've done so far, the string theory side, the other group in TT-bar side, and this the new computation, they agree with each other. And I think my time is up. I'll stop here, and I'll skip over the other part, and I stop at this final page. Thank you.
Do we have questions?
I have a simple question about the non-locality, the notion of non-locality. So it seems like the correlation functions of your dressed operators are the same as the original undeformed correlation functions. And also the dressed Virasoro generators obeys the same symmetry, obeys the same commutation relation. How do you use these to characterize the non-locality? It seems everything is local.
It's in momentum space, and the conformal weight depends on the momentum. So if you want to go to the position space, it's highly non-local. So it has, in momentum space, it has this nice structure of a two-point function, but in order, like, when you do this Fourier transformation, you see this P appears everywhere. The conformal weight depends on P.
I see. So this is for the physical operator, but for the dressed operator, the dimensions are the same as the undeformed.
The dressed operator is the expression of it is highly non-local.
Oh.
It's just that it's inside a correlator. It doesn't change, but itself is I don't know the meaning of this operator by itself.
Thank you.
Questions?
Does H and H bar depend on lambda in the operators you define?
No.
No. So the lambda and momentum dependence here appears after you resum.
Yeah.
You resum all of these terms.
Yeah.
Yeah.
It appears from all this log. You see this combination, lambda pp bar times this log.
Thank you for the talk. My question is more about the string theory worksheet slide. We know that string theory has T-duality in general, I mean ODD type duality, which
Yes.
is much more general than TST. So probably, and this is generating the symmetries of the spectrum.
Yeah.
So can we go beyond TT bar using a more general T-duality transformation?
Yeah, that's definitely interesting. Yeah, so then you can in the bulk you can cook up like more general geometries. I think one difficulty on that is that I'm not sure how much is known about the dual. What kind of deformation are we doing in the CFT side? Maybe you have some results.
So a good past which has been studied is that deformations generated by Yang-Baxter equation.
Yeah.
So that is very well studied, and that's a part of this T-duality transformations on the worksheet.
Yes, that's very very interesting.
We have time for one last short question. Short.
Ground state, right?
Mhm.
If you can you consider thermal state?
Sorry, ground state of
So you put the CFT on complex plane.
at the moment on the plane. Yes.
Yeah, if I consider thermal CFT, I think the manifold has some boundary, has some side. So will this analysis still work?
Well, we just that's certainly interesting to explore it. But all I know is that this barrel, I think the second author here, he studied some correlation function on torus.
Thanks again, Wei Song, for her talk.